Welcome back everyone. Today we learn about work and energy. First, let's learn about work, or work done. Work is done when a force moves an object through a distance in the direction of the force applied. Work done equals force times distance moved in the direction of the force. There are three conditions for work to be done. First, there must be a force acting on object. Second, the object must move. Third, distance moved must be in the same direction of the force. The unit for work done is Newton meter, or joule. The SI unit for work done is joule. 1 joule or 1 Newton meter of work is done when a force of 1 Newton moves an object 1 meter in its direction. Next, energy. Energy is the ability to do work. The SI unit for energy is joule. The law of conservation of energy states that energy cannot be created or destroyed, but only changes from one form to another. There are two major forms of energy: kinetic energy Ke and potential energy P. Kinetic energy is the energy possessed by a body due to its motion. Kinetic energy can be translational, such as a moving car, or rotational, or vibrational. That's why we also call kinetic energy as energy of movement. Kinetic energy equals 1/2 times mass times velocity squared. Another major form of energy is potential energy. Potential energy is the energy possessed by a body due to its height. Potential energy is measured relative to a reference, usually ground level. Potential energy equals mass times gravity times height. There's a special type of potential energy, called elastic potential energy. Elastic potential energy is the energy possessed by a body because of its compressed or stretched state. Let's take a look at how energy transformation occurs on a bouncing ball. Next, let's use a simple pendulum to observe the conservation of energy in action. A pendulum has two types of energy: potential energy, which is stored energy, and kinetic energy, the energy of motion. Together, these make up the mechanical energy of the pendulum system. As a pendulum swings, its potential energy changes to kinetic energy, then back to potential energy, then back to kinetic energy, and so forth. At its starting point A, all of the pendulum's mechanical energy is potential energy. It has no kinetic energy because it's not moving. As the pendulum moves downward to point B, some of its potential energy changes into kinetic energy. At its bottommost point B, the pendulum's kinetic energy is at its maximum because it is moving at its fastest speed. Its potential energy is at a minimum because the pendulum is at its lowest point. The pendulum again gains potential energy as it moves upward to point C. At the top of its arc at point C, it once again has zero kinetic energy and maximum potential energy. Notice that as the swing continues to move, the arcs get smaller and slower. Eventually it stops. What happened to the pendulum's energy? In a word, friction. Friction is a force that resists movement. As objects move against one another, friction changes some of their mechanical energy into thermal energy, or heat. As the pendulum moves through the air, friction from the air molecules resist its movement. This changes some of the pendulum's kinetic energy into thermal energy, which is transferred to the environment. With less kinetic energy, the pendulum slows down. When all of its mechanical energy has been converted to thermal energy, the pendulum stops. It no longer has potential energy or kinetic energy. But the total energy in the system remains the same. Next, we see how to apply what we have learned on several questions. An object of mass 200 gram is moving at a velocity of 3 meters per second. Calculate the kinetic energy of the object. A man picks up a box, 2,000 gram, to a height of 40 centimeters. What is the gravitational potential energy gained by the box?